Hello everyone, I am at the scientific services with our Biotic scientist, yes, Tessia Sprido. So she is going to tell us everything about the lab.
Yes.
Right, so what do you do?
So, basically what I deal with as a biotic scientist is things that do not live or breathe. So those are things like soils, water, climate, and fires. So something that I'm very interested in with regards to this, which are soil samples that are collected in the field around Kruger bridge. And what I was trying to look is to see the moisture content in the soil, which is basically how wet the soil is. So what we do is we take the soil sample in the field and we bring it to the lab, and then we measure the weight of that sample, right? So this is 137 grams at the moment. So what it's measuring is the weight of the container, the weight of the soil, and the weight of the water between the soil particles. And then after we have that, what we consider wet weight, we then put this in a drying oven at 105 degrees for 24 hours, and over that 24 hours, the water then evaporates. So when I measure it again, it has less weight and it's lighter because then the water has disappeared. And that's how we can calculate how much water is in the soil.
Okay, so what exactly are you looking for when you do all these things?
Yeah, so what we were doing here, the soil samples comes from a place where I was looking at soil respiration. So what that is a machine that actually measures how much carbon dioxide comes from the soil. And the reason that the process that's happening that gives up carbon dioxide is that all these soil microbes, all these organisms, bacteria, all the fungi in the soil, when they are actually decomposing and eating roots and other animals within the soil, that activity they give off carbon dioxide. So by measuring carbon dioxide over the soil, you can see either how much soil microbes there are or how active they are. So the reason why the soil moisture is important is because they need water when they are actually decomposing nutrients in the soils.
So where do you take this information? After doing everything that you do, where do you take the information?
So we basically use it because we're interested in actually finding out what is the role of soils and microbes in the landscape. Right? So microbes are very important for, like I said, cycling nutrients, and when they make things like carbon and nitrogen, phosphorus, potassium, all these things available is for plant roots to use, right? So as the plants grow, they need these nutrients. And we are looking at a site that has recently been burnt. So you know that in the savannas, in Kruger, fire is a very important process in the savanna, especially as we head into the dry season now. And it's a way of showing how important fires are to actually put ash into the soil because it makes nutrients from the vegetation available to go into the soil, and then the microbes use that to make more nutrients available to the plants to use as they grow again after the fire, and as the grasses come back.
That is interesting.
Yeah.
All right.
So here we are trying to do a water infiltration test.
Okay.
And basically what we're trying to look at, like when it rains, that it's very important to know how fast water can infiltrate into the soil, right? And if soil takes long to allow rain to infiltrate, that's when you have the risk of soil erosion and loss of topsoil. So it's very important that soil has that capacity to absorb that water. So one easy way of testing that is to actually just take a water droplet, it's called a water droplet test, and you actually time how long that water droplet takes to infiltrate into the soil. And some soils, it can happen within a second, right? Like this one. This is taking like less than a second to go in. So these soils are really good, and no matter how hard it rains, it will be able to absorb that water. But then you get some soils where a water droplet can sit for 60 seconds, just sit in there because the soil cannot allow it to infiltrate.
That's when the particles are closer together.
Yes, so there's maybe two ways in which that happens. One of which is there's actually a chemical process, right? Where maybe there's a certain kind of plant sap or kind of material that coats the soil surface, right? So it doesn't allow it to infiltrate, almost like a bit of like plastic, put it that way. And then the other way is the physical charges of the soil particles. So there's positive and negative, right? So sometimes when the charges of the soil particles are in such a way that it actually repels the water, the charge of the water, so it actually repulses and it doesn't allow it to infiltrate. So there's different ways in which soils can become hydrophobic. But in this case, we do not have hydrophobic soils, which means water-hating soils. So these ones are infiltrating very nicely.
So which one is better for the plants?
So obviously a soil that can allow water to infiltrate But it comes with pros and cons, right? So, like basalts, because it's so fine grained and it's clay soils, they do take longer to infiltrate compared to sandy soils like the basalt, like the granites around Pretoria, Kruger, that's all sandy soils. But the disadvantage comes when, let's say it's dry and the soil evaporates. So the basalts, although they take long to let the water in, they also take long to lose the water.
Oh.
Right? So the same like with the sandy soils around Kruger, Pretoria, etc., it can allow water to infiltrate fast, but you can also lose your water very quickly. And if you think of like as you go into the dry season after the rains, you will have your fine-grained clay basalt soils holding on to water for much longer after the rains, so the grasses are greener for much longer after the rains also.
So how long does it take to finish one research?
Research is one of those things that just never ends.
Oh, okay.
To be honest,
it's continuous.
It's continuous because as you have one question that you're trying to answer, you actually have more questions along the way because you might find one result and then you're like, but why is it like this? What if it's because of this reason? Then you end up asking that question. So always you're continuously learning more and more and more.
So what happens? What happens if you happen to like come up with a new idea or maybe a new topic? Let me say a new topic. Do you stop with the previous research and engage in the new one?
Yeah, generally, especially if it's a slightly different question, research question you're trying to answer. That definitely happens, and sometimes you're working on multiple research projects at the same time.
Don't you get confused?
No, generally not. Generally not. There's many kinds of research projects happening at the same time right now. So my personal project that I'm very involved in is actually trying to look at how fires in the landscape affect soil's ability to allow water to infiltrate and the nutrient content. So I'm trying to see like if you burn differently, if you burn every year, every 3 years, if you don't burn, what kind of effect fires have on soils. And then there's also other research projects where we're trying to look at, like elephants in the landscape. Elephants are very big role players in the landscape. So they knock down trees when they're alive and they pull down branches and then impalas that eat the leaves, and then the rivers, they dig holes in the dry season so that animals can also drink water. So in their lifespan, elephants are big, what we call ecosystem engineers, right? Because they change the landscape. But when the elephant dies and becomes a carcass, we're trying to look at, because that's 6,000 kilograms of animal that dies, what happens to the landscape where they die. Right? So that blood and nutrients that go into the soil, does it change the soil chemistry? What nutrients then gets made available? How does that impact the plants that grows? So that's also some of the research that we look at, and that's all related just to soils.
So do you always work in teams or individually?
Always, yeah.
Always.
You can never, there's only so much you can do alone, but together you can do so much more.
Oh, okay.
Yeah. So we're always a team of maybe a soil scientist, a plant person, a climate person, an animal person, and we all try to bring our different skills together to answer one big question.
Okay, so I see an oven here. Is it for the staff? Do you use it for like your science projects or something else?
So this is what's called a drying oven. It's not like an oven to bake birthday cakes.
Okay.
This is the science oven. And it can go up to about maybe not more than I think like 200 or so degrees. Doesn't it very, very hot?
It gets hot.
Okay, it's hotter than your normal oven. It might go up to 600, I'm not too sure exactly. But anyway, what the temperature I needed at is at 105 degrees. So once they get the wet weight of these samples with the water still between the soil particles, I then put it in the oven at 105 degrees for 24 hours. And then basically within that 24 hours, the water is evaporating. So by the time I weigh it again, it will be without the water. So that missing value in the equation is how we calculate moisture content. And you will see that with each site that we measure, we never just take one sample. We always take more than one sample because sometimes the measurements, you can get a range of values, right? And you know with maths, you need to get the average.
Of course.
So we need to get the average or the mean, so we always have multiple samples.
So how do you know that you need 105 degrees Celsius for the soil and also 24 hours?
Yes, so the thing with the science, it's almost like a recipe that you follow when baking a cake.
Oh, okay.
Right, so over the years, way that people know what's the ideal method to get you the right answer. Like they've run this many, many times and they've seen that 105 degrees at 24 hours is the best temperature and time that's needed to evaporate all the water. If I ran it at 50 degrees Celsius for 24 hours, there might still be water in the soil, but 105 is ideal to get all that water out. What's quite interesting with the soils is that different kinds of soils hold on to moisture very differently. So like your sandy soils that you'll get in a riverbed, for example, that doesn't, because the size of the sand is so big, it doesn't hold on to water nicely, right? So the water will just move right through it. Same for when it evaporates, it can evaporate easily through it. But you'll find the soils like your clays, which is very fine grained soils, they hold onto moisture much, much better. So even right now in the park, if you go onto the basalts towards lower side of Crocodile Bridge, that soil is still wet. And if you think about the last big rains we had was a couple of Feb, March. But if you go towards Victoria Scope, that side where the soils are more coarse and sandy, it's already much drier.
Okay, so you said you keep it in here for 24 hours. Is there somebody who keeps it up or you very sure that nothing will go wrong?
Very sure. This is a good oven and I'm sure it'll stay at 105 degrees because we set it at that temperature. And even if there's load shedding and the power goes off, it remembers that it was set at 105, so we'll go back to that.
It continues.
Yeah. And then it will only go off when I come back. So I know which date and time I put it in. And I'll make sure I come back tomorrow at the same time to switch it to position. Yeah, and to measure it again.
Alright, that was very correct. Thank you so much.
Cool. Thank you.
Alright.